Automation, modes of control. The fusion of dynamic adaptation and control architecture. Automation in the modern process industry represents more than just mechanized action. It embodies an intelligent framework that dynamically responds to changing process variables, load conditions, and performance targets. Adaptive control, as a principal mode, enhances automation through real-time parameter adjustments, ensuring process stability and optimality even as external or internal conditions shift. Redefining control in the age of adaptation. At its core, adaptive control is a self-modifying mechanism. Unlike fixed gain or statically tuned control strategies, it evolves its internal parameters in response to deviations in process characteristics. This mode offers superior resilience by maintaining consistent loop gain, countering load upsets, and ensuring optimized control of dynamic systems. The result is a control environment that continuously conforms to changing demands, yielding accuracy, speed, and efficiency. Three primary modes of adaptation in automation. Programmed adaptation, gain scheduling. Based on known relationships between a process variable and the process gain, the controller settings are adjusted proactively. For instance, in large capacity heat exchangers or critical level control systems, the process gain may vary with operating set points. The control algorithm is preloaded with different PID, proportional integral derivative, settings across operational thresholds, enabling a quasi-open loop adaptation that simulates intelligence by predefining controller behavior across changing operating zones. Here, the controller adjusts its parameters based on measurable load disturbances before they affect the process. In thermal systems, for example, as the flow of feed water load increases, the dead time and steady state gain change. The controller adapts proportionally, increasing or decreasing PID parameters to preserve a stable period of oscillation and consistent damping. This form allows predictive shaping of control dynamics by aligning controller aggressiveness with real-time process inertia. Feedback adaptation. This closed-loop strategy involves direct modification of control actions based on observed process output deviations. A classic use case involves pH titration systems, where nonlinear gain regions fluctuate. Through periodic assessment of process behavior, such as oscillation patterns or sluggishness, controllers can self-modify their internal parameters, such as dead bands or gain profiles, to restore balance and precision. Structured control layers incorporating adaptive intelligence. Regulatory layer, base control, maintains direct process variables, temperature, pressure, level, using adaptive PID elements. It ensures fast corrective action at the sensor-actuator interface, responding immediately to load and set point changes. Adaptive compensation layer acts as an intermediary, modulating the PID parameters based on process modeling and real-time operating conditions. This includes handling dead time, gain variation, and cross-variable interactions through multivariable adaptation. Supervisory layer, optimization, and fault handling. Integrates economic objectives, fault diagnostics, and constraint management using AI, artificial intelligence, pattern recognition, and soft sensing technologies. It enables real-time reconfiguration of control logic for energy savings, product quality enhancement, and emissions reduction. Core features of adaptive automation. Process gain and dead time modeling. Using empirical or first principle models, adaptive control systems understand how gain and delay characteristics shift with operating conditions. These models guide parameter recalibration. Normalized flow-based tuning. Adaptive PID algorithms factor in normalized load measurements, e.g., 0 to 1 range from flow transmitters, to dynamically tune controller aggressiveness. For high load, low process gain, more aggressive control is needed. For low load, high process gain, smoother adjustments are favored. Integral and derivative scaling. Time constants for integral and derivative action are auto-scaled with load, ensuring constant damping ratios and loop stability across varying throughput levels. Pattern-based feedback correction. Advanced feedback adaptation systems use oscillation frequency and damping trends to modify gain or dead band parameters, reducing reliance on manual retuning or operator intervention. Key technological enablers in adaptive control automation: real-time soft sensors and inferential estimates, microprocessor-based self-tuning controllers, digital signal processors for high-speed response, AI-driven rule engines for pattern learning and fault detection, OPCU and modern data buses for seamless integration, simulation and digital twin environments for dynamic testing, cybersecurity protocols embedded in control logic to safeguard integrity, transformational benefits across industrial sectors. Stable, operations under fluctuating load and process drift, better energy utilization by adapting to real-time thermal demand, minimization of manual tuning and operator override, enhanced product quality and process consistency, greater agility in batch and continuous process environments, reduced process oscillation, fewer alarms, and increased uptime. Conclusion: automation, when augmented by adaptive control strategies, becomes a dynamic partner in industrial performance. Rather than merely executing commands, it senses, learns, and evolves. Through programmed feedforward and feedback adaptation modes, modern controllers mimic human-like intelligence, achieving operational excellence not by brute stability but through responsive precision. This intelligent automation architecture forms the foundation of future-ready, data-integrated, and resilient industrial ecosystems. All the files uploaded by the user have been fully loaded. Searching won't provide additional information. Cascade control, multi-layered defense against process disturbances, optimizing response through hierarchical loop structuring. Cascade control represents a layered automation strategy engineered to address both load and supply upsets with enhanced responsiveness and precision. By nesting a fast-acting secondary control loop within a slower primary loop, cascade control ensures that disturbances are corrected early in the control path, preventing their propagation to critical process outputs. Fundamental structure of cascade control. At its core, cascade control configures two interlinked feedback loops. Primary loop, master outer loop, controls the key process variable, e.g. temperature, level, composition, and determines the set point for the secondary loop. Secondary loop, slave inner loop, directly manipulates the actuator, typically a control valve, to regulate a fast-changing intermediate variable, e.g. flow or pressure. The primary controller governs strategic objectives, while the secondary controller tactically reacts to rapid fluctuations such as valve friction, supply pressure changes, or mechanical hysteresis. Dynamic response to supply and load upsets. Supply upset. When steam header pressure drops, flow is disturbed despite a constant valve position. A standalone primary loop may fail to stabilize under frequent supply variations. Cascade configuration addresses this by allowing the secondary loop to react instantly to flow deviations and restore the desired actuator behavior. Load upset. A sudden demand change alters heat or mass transfer rates. The primary loop handles this through gradual corrections, while the secondary maintains process continuity and isolates fast dynamics. Performance criteria for effective cascade deployment. Cascade architecture succeeds under specific timing conditions. Period ratio requirement. The primary loop must be significantly slower than the secondary loop. A practical period ratio, frac T primary T secondary, GKEEK 4, ensures minimal phase interference and clean loop decoupling. Loop gain and phase compensation. For an ideal cascade configuration, the secondary loop should behave as a unity gain, zero phase element when viewed from the primary loop. This minimizes distortion in the control path and preserves tuning integrity. Benefits of cascade control. Elimination of supply-driven variability. The secondary loop intercepts and neutralizes supply perturbations before they reach the core process, enhancing output stability. Reduction of integral absolute error, IAE. By shortening response periods and reducing phase lags, cascade control minimizes the cumulative error from set point deviations or process disturbances. Improved control of nonlinear actuators. Secondary loops with valve positioners mitigate hysteresis, dead band effects, and nonlinear flow characteristics, especially cascade control, multi-layered defense against process disturbances, optimizing response through hierarchical loop structuring. Cascade control is an advanced automation strategy designed to tackle both load and supply disturbances with increased agility and precision. It does so by embedding a fast-responding secondary control loop within a slower primary loop, allowing early correction of disturbances before they propagate to critical output variables. Architecture and functional roles. The cascade structure is built around two interdependent feedback loops: primary loop, master, or outer loop. This loop focuses on controlling the main process variable, such as temperature, level, or composition. It sets the desired target for the secondary loop based on broader operational goals. Secondary loop, slave or inner loop. Operating at a faster rate, the secondary loop directly controls the actuator, typically a control valve, by regulating an intermediate variable like flow or pressure. Its role is to quickly respond to fast dynamics and stabilize the manipulated input. While the primary loop provides the strategic directive, the secondary loop delivers tactical precision, responding immediately to fast disturbances such as supply fluctuations, valve friction, or internal process variability. Managing load and supply upsets. Handling supply upsets. When the energy or material input, such as steam pressure, fluctuates, the flow rate can deviate significantly, even if the valve position remains constant. Without cascade control, this disrupts the process output. With cascade architecture, the secondary loop swiftly corrects the flow, maintaining stability in the primary variable. Handling load upsets. Sudden changes in demand, for example, shifts in feed rates or heat transfer requirements, affect the system's output. While the primary loop addresses these more gradual disturbances, the secondary loop preserves control accuracy during the transient phase. Timing and responsiveness. For cascade control to function effectively, the secondary loop must be significantly faster than the primary loop. This ensures that the inner loop can neutralize disturbances before they affect the outer loop's measurement and control decisions. Gain and phase management. The secondary loop must act transparently from the perspective of the primary loop, responding with minimal delay and distortion. This allows the primary controller to operate as if directly manipulating the final control element without needing to compensate for secondary loop dynamics. Operational advantages: resilience to supply fluctuations. Cascade control intercepts and corrects disturbances in the supply system, such as pressure drops or valve nonlinearities, before they affect the process output. Improved stability and accuracy. By reducing lag and isolating disturbances, cascade systems lower the total accumulated error, leading to tighter process control and more consistent product quality. Compensation for nonlinear or difficult valves. Secondary controllers, including valve positioners, compensate for issues like hysteresis and dead zones, ensuring that actuator movement aligns with the control intent. Implementation insights. Secondary loops as high-speed guardians. Flow and pressure loops often serve as secondary elements due to their fast response characteristics. Their proper tuning is essential before enabling the primary loop. Tuning strategy. The secondary loop is tuned first in isolation, using wide proportional bands and fast integral times for responsiveness. Once stable, it is linked to the primary controller, which is then tuned to accommodate the dynamics of the entire cascade structure. Startup and wind-up protection. Wind-up in the primary controller is a risk if the secondary loop is disabled or constrained. This is mitigated through external feedback mechanisms or anti-wind-up strategies, ensuring that the primary loop only integrates valid control actions. Application versatility. Cascade control is broadly applicable across heat exchangers using temperature-on-flow configurations, exothermic reactors with temperature-on-temperature setups, level systems with valve position cascades, systems prone to supply disturbances or nonlinear actuator behavior. Summary. Cascade control provides a strategic method to compartmentalize control responsibilities across loops of differing speeds. It enhances stability, compensates for actuator imperfections, and fortifies systems against disturbances, offering both resilience and performance in complex industrial environments. Integrating cascade control within adaptive automation frameworks. Combining multi-layered defense with self-tuning intelligence. Adaptive control and cascade control, while distinct in mechanism, are highly complementary in modern automation systems. Cascade control delivers structural resilience against fast disturbances, while adaptive control enables continuous tuning of controller parameters to maintain optimal performance in the face of process variability. Their integration creates a dynamic and responsive control strategy, capable of both fast correction and long-term adaptation. Converging strengths. Structural hierarchy meets dynamic tuning. In a typical cascade setup, the primary loop governs a slower, more strategic variable, e.g., temperature or composition, while the secondary loop controls a faster responding intermediate variable, e.g., flow or pressure. By embedding adaptive functionality into either or both loops, the system gains the ability to self-correct not only in terms of output, but also in control configuration. Adaptive secondary loop. The inner loop, such as a flow controller, can be enhanced with adaptive mechanisms that adjust PID settings based on real-time load conditions, valve wear, or supply fluctuations. For instance, a feed-forward adapted flow controller can scale its gain and reset time in response to changing steam pressure, ensuring fast recovery without overshoot. Adaptive primary loop. The outer loop, often regulating product quality variables like reactor temperature, can implement feedback-based adaptation. This allows the primary controller to shift its tuning dynamically as the process gain, dead time, or operating regime changes, ensuring the cascade structure remains robust under varying conditions. Benefits of adaptive cascade integration. 1. Improved loop decoupling under variable dynamics. Adaptive tuning maintains the necessary timescale separation between the primary and secondary loops. As secondary loop dynamics shift, e.g., due to valve stiction or header pressure changes, adaptation preserves fast loop responsiveness and prevents interference with the slower primary loop. 2. Sustained optimality across operating envelopes. Whether process gain increases with flow rate or dead time lengthens during startup, adaptive elements in each loop recalibrate controller parameters in real time, ensuring that the cascade remains properly damped and aligned with performance goals. 3. Enhanced resilience to supply and load drift. Supply upsets, typically addressed structurally through the cascade, can be further mitigated when the secondary loop adaptively tunes to shifting steam enthalpy or header dynamics. Likewise, adaptive correction in the primary loop prevents performance degradation from catalyst aging, fouling, or feedstock variability. 4. Protection against loop saturation and wind-up. Adaptive controllers can include intelligent anti-wind-up schemes that recognize when the secondary loop is constrained or manually overridden. The primary loop can suspend or scale down its integration to avoid driving the system into saturation, a frequent risk in cascaded systems without adaptive coordination. Implementation patterns. Programmed adaptation in secondary loop. Controllers use load-dependent scheduling, e.g., based on normalized flow transmitters to predefine gain, reset, and derivative values, perfect for flow loops embedded within cascades. Feed-forward driven gain adjustments. In heat exchanger cascades, adaptive elements can interpret changes in condensate temperature or inlet enthalpy as triggers for retuning the flow controller, thus compensating for variable thermal inertia. Feedback-based pattern recognition in primary loop. The outer controller monitors oscillation patterns, damping trends, and process drift, adjusting control aggressiveness accordingly. This ensures stability as the process deviates from the baseline model. Design considerations. Maintain a clear speed hierarchy. Adaptation must not erode the relative responsiveness of the secondary loop. Use external reset feedback to prevent primary wind-up during secondary loop saturation or manual mode operation. Validate that adaptive gains remain within safety and stability margins, especially during startup and transition phases. Conclusion. By embedding adaptive control principles into the Cascade architecture, automation systems gain dual-layer intelligence. Structural isolation of fast dynamics via cascade and continuous parameter refinement via adaptation. This synergy enables industrial control systems to maintain optimal performance across a wide range of operating conditions, disturbances, and process shifts, delivering both responsiveness and resilience in a unified framework.